running installation of Python as scikit-learn in order to follow the lab classes. The first lab class will be next Wednesday. It's okay?
Yes.
We will announce it properly, but just to remind you. Okay? We don't know. The only thing we know is that all teaching is going to be online in February. What is going to happen in March? I don't know. Quite likely, theory classes would remain online, at least in March. Probably, but I don't know. Huh? And lab classes, I don't know. Okay. Okay, so in the last classes, we were, okay. Okay, in the last classes, we were talking about the formulation and parametric approaches. Mainly, we introduced the Bayes classifier, which can be seen as the ideal classifier if we would have the whole information about the problem. We never have this whole information. Even if we have a lot of data, which sometimes may happen, even in this case, we can only work with very rough estimates of this whole information. So the Bayes classifier is nothing but an ideal, a concept. Nevertheless, the Bayes classifier can be implemented if we make strong assumptions, as, for example, if we assume that the classes are Gaussian. And from these assumptions, we arrived to the linear classifier and to the quadratic classifier, which are the one we introduced in the last class. Okay. Following a rather different approach, we are going to introduce what we call distance-based methods. Take into account that we, in some cases, for example, in the Gaussian case, we related the classifiers, we related them to the concept of distance. In that case, the Mahalanobis distance. Well, now we are going to talk about distance in general. Of course, we are going to relate as much as we can these methods with the previous methods we introduced. But we start from a rather different approach. In the first place, we assumed known shapes of the distributions of the classes, and then from that we follow a statistical approach, let's say, and now we start from some given distance. If someone gives us a way of assessing how close or how far two different examples, two different inputs are, just with this way of measuring closeness, what can we do? So that's the starting point of what we are going to study today. These distance-based methods are inside what we call non-parametric approaches. Why non-parametric? Because we do not assume any form for the distributions. We are going to have parameters. We always have parameters, but when we say parametric or non-parametric, we refer to the parameters of the distributions. So we assume we have no distributions at all. Even if we have, we ignore them. It's okay? So we make no assumption about the underlying statistical structure of the problem. Non-parametric methods are closely related or very close to what we call multimodal problems, because multimodal means that we have more than one clear representative for each class. Why multimodal cannot be efficiently tackled by parametric approaches? Because we start needing too many of them if we have more than one mode. So when our problem is such as complex as that we can have for a given class like different ways for realization on this class. For example, imagine in the slide the digits problem. If we are going to characterize written digits, for example, 1 on the left, 4 on the right, clearly we can write 1s and 4s in different ways. In most of the representation spaces we can think of, it's quite likely that both classes have different representatives, different modes, something like what we have in the bottom of the slide. So it's quite likely that each of the classes have several modes corresponding to the different ways in which we can write each of the two digits. Okay, we are simplifying the problem. We are writing the distributions in one dimension, and this is nothing but a toy example. But I mean, this is the idea. Of course, as we commented, because we ended the last class talking about semi-parametric approaches, we can always break any multimodal problem into a mixture of several unimodal problems that can be tackled appropriately using parametric methods. But I mean, this is not what we are interested in now. Okay, if we do not assume any particular form in the distributions of data in the representation space, what we have? Well, what we have is just data. And when we have just data with no assumptions, what can we do? Or at least from the point of view of non-parametric approaches, or what it has been traditionally called non-parametric approaches. Well, we have mainly two very basic approaches. The first one is to assume something about the classifier itself. For example, let's assume my classifier is a linear function. So my possible classifier is any linear function. How many parameters has a linear function? Well, basically one parameter for each dimension plus a bias. Well, these are the parameters of my classifier. Then I can try to obtain which is the best linear function that separates my data. Even though I'm obtaining a linear classifier, and if I follow a parametric approach and I assume the classes are Gaussian, then I compute means, and then I compute a linear classifier, these two linear classifiers are very, very, very different. In the first case, I make no assumptions and I have a broad optimization problem. In the second case, I have a closed form methodology. I estimate distributions. From that parameters, I compute a linear function. So the final product is the same. The method is different. It's okay? Linear classifier is just one of the possibilities. We can think of any other form for my classifier and then pose the same problem. Obtain which are the parameters of my classifier that best separate my training data. In particular, this is the approach that is followed in the case of neural networks. Okay? So we will arrive there, but anyway, we fix a particular architecture for a neural network with, let's say, a huge amount of parameters, and then my problem is to find which are the parameters for this network that best separate my data. This is one of the approaches in the from the non-parametric point of view. And the other one, classical one, is to obtain, to fix, to obtain, to design a particular measure of similarity or dissimilarity, I mean, a distance, and then use this distance to decide about the classification of each input sample. Okay, so the approach we are going to explain to get into in this class is the second one. The advantage of this approach, well, we have, as always, we have some advantages and some disadvantages. The first advantage is that the criteria to decide the class using distances is very clear and very natural. If two inputs are close enough, then it's quite likely that they belong to the same class, isn't it? I don't know if you are here. Please say something from time to time. It's okay?
Yes.
Okay. Yes. Okay. So, as I was commenting, if two examples of something are close enough, then it's quite likely that they belong to the same class. Well, but what does it mean? What means being close enough? Well, for non-trivial problems, for non-trivial problems, what we have, perhaps, is a complex representation. Perhaps we have a vector of features, of many features. Close means that there is a measure of distance. In principle, the more natural distance is the Euclidean distance, but not necessarily. But anyway, let's consider the Euclidean distance. Just to use an example, imagine a two-dimensional space like this, and then all possible inputs for a given problem is just a point in this plane. So if I have 2 points which are close, so quite likely they will belong to the same class. Or these two. It's okay? But I mean, not necessarily this measure of closeness directly translates into being or belonging to the same class. It's just an idea. It's okay? Moreover, to be able to convert this into a classifier, I will need to attach, as always, to attach a label to each training example. So if I know what's the input for examples of a given class, I can compare any possible input to the examples I have in my system. So, and then I can assign classes according to what I have in the memory. So this is going to be more or less the idea on this family of classifiers. But first of all, let's think about what in fact this distance means. Well, is really the Euclidean distance a good measure on how close, in fact, two inputs are? Well, this is a tricky question, and there is no easy answer for that. But you have to realize that distance can be a bit misleading. For example, if we have a representation space, let's say as the one here, and we have 3 different outputs, we can clearly see that these two are closer between them than if we compare this distance to the distance to the third point. So we could think that, well, maybe these two belong to the same class and this could belong to a different class. But I mean, what happens if we change this representation space to another representation space in which the only difference is that we have scaled one of the features? So instead of measuring these values in this dimension in 1 unit, I don't know, let's say millimeters, let's say we measure now in meters. So then we have this. And now these 2 points are much closer, just changing the scale. You see?
Yes.
Okay. Of course, in particular problems, we can think of ways of obtaining some sort of invariation to scale or something. But I mean, it's just to illustrate how weak this concept can be when considered in this way. As I was saying, methods based on distance have pros, advantages, and perhaps the most important are interpretability and perhaps also the possibility of using more abstract spaces. I mean, we are not restricted to representations which have dimensions. We can measure distances between anything. For example, distances between strings, distances between graphs, distances between text files, etc., etc. If we can measure distance, we can classify just with these distances. Okay? But then probably the most important disadvantages are these dependencies on the changes of space, or, which is quite related, the dependence on the particular metric. Because using one definition of distance, we can have one result. Using another distance, we can have a different result. Which is the good one? Well, difficult to say. It's okay? Just a summary of different distances that can be used. Well, by default, we can use the Euclidean distance on vector spaces once we have our data appropriately normalized or not. This Euclidean distance generalized to the so-called Minkowski family. The Euclidean distance is called also the L2 distance. We have the L1 distance, and in general the LP distance, which are generalization on the Euclidean distance. All, for example, in the Euclidean distance, the distance from a given, I don't know, sorry. In the Euclidean distance, the distance from a point, as we move from one point, then we move like this. So the places that are at the same distance are hyperspheres. It's okay. And the family of Minkowski, the Minkowski family, is something like this. Let me, how it was. So as we move from one point, then the points of the same distance are things like that. We have also the L infinity. Okay. The other type of distances we have is the Mahalanobis. Mahalanobis distance in general are distances in which when we move from one point, then we obtain things like that. It's okay? When we say Mahalanobis distance, strictly speaking, we are talking about distance from any point to the mean of a Gaussian distribution. And then this distance, the shape of this distance depends on the covariance matrix of this distribution. But in general, when we say Mahalanobis distance, in general, is because we have a matrix A. We have a matrix A that takes the role of this covariance matrix. So no matter which matrix is this, as long as it is semi-definite positive semi-definite, sorry, and then we have a distance which is measured like this. We also have what we call weighted distances. Well, a feature weighted distance is nothing but the particular case of a Mahalanobis distance in which we weight separately each of the features of the dimensions. Then what we have? Well, in that case, we have distances like this because we weight more x1 than x2, or like this, in which we weight more x2 rather than x1. So these two are particular cases of what we call Mahalanobis distance. Weighting the dimensions is the same as changing the scale. You see?
Yes.
Okay. Not as usual, because this is quite usual, this Euclidean or Minkowski distances and Mahalanobis or quadratic distances. These are quite usual. Not so usual are what we call prototype weighted distances. What this means? Well, it means the following. Imagine I have a problem and I have several examples. And then I assign different weights for different examples. These weights control how distances are measured. For example, if I have a input at this point, when I measure the distance to example 1, I measure the distance multiplied by a value. When I measure the distance to these two, I multiply this by another value, another weight. For example, this, which has the greatest weight, then, for example, imagine that when I measure the distance from here to here, then this is at distance 1. And when I measure the distance, this is the x2, x1, sorry, 3. When I measure the distance to prototype 1, then because the weight is smaller, then this is a distance 2. So I selectively use different distances when measuring distances from different points. In fact, I should have plotted the other way around. I mean, I could have drawn the distance from this like this, and then the distance from this like this. It's okay? And this one even with less weight. Do you see? These are called weighted distances, which is something similar to what we call local distances. Local distances, it's opposed to what we call global distances. All of these are global distances because the distance function this distance function, it's a unique function. It's the same function for the whole space. What is a local distance? Well, a local distance is a function that depends on where it is applied. You see? A global function for the whole space, a different function for each point of the space. It's okay?
Yes.
Okay. Well, so let's go into some details. Any questions about distances? I don't know if you were familiar with Minkowski distances.
Not me.
No? You've never heard about the Manhattan distance?
Yes.
Manhattan distance is one case of a Minkowski distance. Minkowski distances are this is the Euclidean distance. Isn't it?
Mm-hmm.
Or written in another way. Oops, well, there's something missing here, isn't it? Now, okay? Do you agree?
Yes.
No.
Mm-hmm.
So, in general, the Minkowski family is this expression. But this expression, when p tends to infinity, then what we have is this, which corresponds to measure the distance from one point to another point as the well, this is one of the options. This is not the Euclidean. The other option, the two limit cases are that one and also the other one, which is the sum of this. This is, for example, measuring the distance as the sum, sorry, the sum of this. This is the Euclidean distance. This is the L1 distance. And in this case, if this one is greater than the other, then this is the L infinity distance. So these are all the ways we can measure distances between 2 points using this Minkowski family, whose general formula is something like this. Just have a look and because I mean, most of the methods we have implemented for example, in scikit-learn, have the possibility of fixing this p parameter. Okay. Okay, we have more options like any pseudo distance. I mean, all these possibilities here are mathematical distances. I mean, they hold several properties, but I mean, we don't need that the function we use hold any mathematical property. So we can use any value we can obtain from 2 input points, provided they mean something. Okay. And any other computation we can do. It's okay. Questions? No? Okay, so we are now going to define the first basic classifier using distances. In this slide, we call E the representation space. I mean, we are not using X because we will assume that when we say X, we are thinking of coordinates. But we do not need coordinates. I mean, we only need distance. So imagine that E is an abstract space for which we have a distance function. It's okay? The other thing we need is to have one example for each class. So if we have C classes, then for each one of those, we have a prototype, an example, a representative. We assume that this example is truly representative of the whole class. The set P formed by all these prototypes and its corresponding label is what we call, as usual, the training set. But I mean, in this case, we have only one example per class. It's okay? These are points from the same space, and the classification space is the space formed by the C labels. Okay? Then we can state the minimum distance classification rule, as it's called, as follows. Any input X belongs to class I if and only if the distance from the prototype, distance from X to the prototype of class I is smaller than the distance to any other prototype from other classes. If this happens, then we assign X to I. Okay? This rule goes like this. I mean, we have an input. We have here our rule. We need the training set here. When some input points enters, then we check the training set, and then we decide whether we answer class 1 or class 2 or class C according to this. It's okay? Very, very, very simple. If I want to separate between cows and horses, I just need one cow, one horse, and whatever I have at the input, I just compare. Is this closer to my cow or is this closer to my horse? Whatever it is closed, then I say, okay, this is a horse or this is a cow. Very, very, very easy. Very, very, very simple. Perhaps too simple. Let's explore what happens with this classifier. In the particular case of a vector space, we can take these distances, distance for each of the prototypes, and develop this. This is for the Euclidean case, Euclidean distance. And then, because we are comparing distances, as you see, we are comparing distances. We are like computing minimums. If you remember, when we defined the discriminant functions, we used discriminant functions for different classes, and then we were computing maximums. Here we are computing minimums. So this comparison is very, very related to the comparison we had for the discriminant function. So we can write discriminant functions here equivalent to this rule. To do that, we develop this, and if we are going to compare this distance from other distance from another class, we have here terms. First of all, we can get rid of this square root. Why? Because this function is monotonous. To compare which one is greater, we can suppress this in all my comparisons. Second, we have here a term which does not depend on I. As it does not depend on I, we can check this out at both sides. You see? What we have left? We have left this. If we change the sign of this, we have a discriminant function. Now we will compute the maximum because we have changed the sign here. It's okay? What this shape of the discriminant function means? Well, this is a linear function. If discriminant functions are linear, it means that the classifier is linear. Deciding the class according to the minimum distance is equivalent to a particular linear classifier. An example here, 1, 2, 3, and 4 classes. And if we compute these functions, these linear functions for all classes and compare them, then we have this boundary between these 2 points, these 2 classes, Remember that there is only one example per class. This is the boundary between these two classes. This between these two classes. This between these two classes, and this between these two classes. You see? Questions? Questions?
No questions.
What about the boundary between these two classes? Because, I mean, let's say this is class 1, 2, 3, and 4. There is a D1 discriminant function, and there is a D4 discriminant function. Because this line corresponds to this. D1x is equal to D3x. This equation gives me this linear function. So what happens between classes 1 and 4? Well, the boundary between 1 and 4 is more or less this. The only thing is that this boundary between classes 1 and 4 is of no use because between class 1 and class 4, we have classes 3 and 2. So the whole classifier, this equality, is not used to classify. I don't know if you understand that. It's okay? At the end, the space, the representation space gets separated in 1, 1, 2, 3, and 4 regions that corresponds to the point which are closest to classes 1, 2, 3, and 4. And the shape of these boundaries depend on how the classes are distributed here. And some boundaries are like active, like this 1, 3, or this 1, 2, but not, for example, the boundary between 1 and 4, because it's not used ever. Okay? This minimum distance classifier is equivalent to the nearest mean classifier, which is also the linear classifier we studied in the parametric case when the covariance matrices are the identity. When covariance matrices are assumed to be the identity, then computing the linear classifier corresponds to taking the minimum distance classifier. In fact, In fact, the problem with this minimum distance classifier is that we usually have more than one example per class. So, and we only need one. What shall we do? Well, we can take a random one, or much better, we can take the mean as the representative. And then we have something very, very similar. This classifier is as simple and as bad as the linear classifier itself. Okay? So it's very, very simple. Okay. But anyway, it's the first step. The second step is to get to a generalization of the minimum distance. This generalization, which starts to be a more appropriate classifier, is what we call nearest neighbor classifier, which can be formulated in the following way. As before, we have an abstract space, and now instead of one prototype per class, we have for each class, we have a set of prototypes of size capital N sub I. Then the training set is just the union of this capital Pi. It's okay? With this modification, the rule now, the nearest neighbor classification rule, is as follows. A given input point X belongs to class I if and only if the distance to the set Pi is smaller than to the set of any other class J. Remember that the distance from a point to a set is defined as the minimum of the distances to the set. So what this rule does is, let's take the whole training set, let's measure the whole set of distances, let's measure distances to any example in the training set, and then keep the minimum. The minimum of the minimum is the minimum. So you take the minimum distance, the nearest neighbor, okay? And then assign as the class of the input the class of the nearest neighbor. Okay? Okay, without entering into details, the analysis of this rule in the Euclidean case is exactly the same as before. Now we have 1, 2, 3, 4, 5 prototypes of class 1 and 1, 2, 3 prototypes of class 2. So we have 2 classes, C equal to 2. But we can think of each of these examples as if it was a different class. Then we have the minimum distance classifier for 1, 2, 3, 4, 5, 6, 7, 8 classes. And then we can plot all these boundaries. You see? And from these boundaries, I mean, as this, and this belong to the same class, at the end, the real boundary is that one. So this would be the boundary of the nearest neighbor classifier. It's okay? So any input at this side of this line is closer to a prototype from this class than prototypes from the other class. So at the end, this is the boundary between these two classes. Okay? Is that clear? Any questions? Mathematically, the expression is the same kind of distance functions, discriminant functions, the same kind, but then there is a maximum that goes through all the prototypes of each class. And then instead of a linear function, what we have because of this max is a piecewise linear function, as you can see. Piecewise between each two classes. Because this is a piecewise linear function. This one is not a piecewise linear function. I mean, between any two classes, for example, between class 1 and class 2, we have this linear function. Between 2 and 3, we have this linear function. So the functions are truly linear. We draw this, but this is a combination of the distance of the boundaries from all pairs of classes. Okay. So linear, and this one is piecewise linear. It's okay because of this max here. Questions? Time is it? Perhaps it's time for a break. Yes. 5 minutes break. No questions at all. You think about questions when we come back from the break.
Okay.
Okay, 5 minutes break. Okay, let's go on. Okay, questions? Any question? Okay, now let me introduce some concepts that are important to when we are talking about distances and minimum distances and nearest neighbors. Is what we call in general proximity structures. If we have a set of points in a particular space, we can define a region in the space associated to each point in this particular set of points, which is called the Voronoi polytope corresponding to the point Pi. We have a set capital P of points, Pi, n of such points, and the Voronoi polytope at Pi associated to Pi with regard to capital P, of course, is formed by all points of the space that are closer to Pi rather than any other Pj of the same set. In other words, all the points that will be classified as I class by the minimum distance classifier, if each point corresponded to each class. This is called the Voronoi polytope at Pi. For example, here, if all of these are our points, forget now about classes, then this region of the space is the Voronoi polytope associated to this point. In this case, as we have two dimensions, this is a polygon, but in general, in any number of dimensions, polytope. It's okay? This other one is a Voronoi polytope associated to this point. Do you agree? And which is the Voronoi polytope associated to this point? Would be this region, or not? What happened here?
It has no limits at the bottom and at the right, only the boundaries with other classes, right?
Okay, so this is an open polygon. So this is an infinite region. It's okay? You see? The polytopes can be closed or can be open. In any case, all of them will have a fixed number of sides or faces, a fixed number of faces, and the region itself is a convex region. Has to be. This is a convex polytope, but it can be closed or it can be open. You see? You see?
Yes.
Yes.
Okay. How many closed polytopes do we have in this example? How many closed polytopes do we have in this example? One?
I think there are three because the top one is the left and right boundaries are like getting together in some point outside of the plot. No?
Do you all agree? Do you understand what he is saying? he's saying that this line and this line, I don't know when, but I mean, let me approach it a little bit. But it's quite clear that these two lines at some point will close this polytope. You see?
Yes.
Any other one? All the others are open. Okay? So in this example, we have 3 closed polytopes and 5 other ones which are open. All of them corresponds to particular cases of this definition. Okay? Okay, as we have defined these polytopes as closed regions, the boundaries are contained into the region, then we can define, it is defined what we call the Voronoi diagram of the set P as the intersection of all Voronoi polytopes. This intersection is in fact the boundaries of the corresponding minimum distance classifier, exactly what we have plotted here in blue. Well, this is just a window because you already know that this goes. Okay? This is what we called the Voronoi diagram of the set P. Okay? These are just definitions. But I mean, you are supposed to know what these definitions are and what these definitions mean. Okay? What would be the Voronoi diagram of a set like this? How would be this Voronoi diagram of these 6 points? Any idea? I don't know. Perhaps something like this? Do you agree? It's okay? Is it like this or not? I don't know if someone is answering. What about imagine that these points are in a circle. What would be the Voronoi diagram? Do you agree?
Yes, I
No
think.
question? Hmm?
I think I do agree because it fits the intersection of the Voronoi polytopes. We should get a graph like this, right?
Okay, that's what I'm asking you, whether you understand or not. I mean, this point here is at the same distance from all the red points. Hmm? The points in this line are at the same distance of these two red points. The same of this line between these two, and so on. Hmm? And in this case, it happens the same. This point is at the same distance of these four red points. And this point here is at the same distance of these 4 points. So these are just examples of Voronoi diagrams of some specific sets of points.
Okay.
Okay. What's the dimension of the Voronoi diagram? What's the dimension of this blue region here, or this blue region here, or this blue region here? What's the dimension?
It's two-dimensional.
Well, it lives in a two-dimensional space, but I mean, when you draw a line in a plane, what's the dimension of the line?
One dimension.
Is 1. And what's what we have here? These are piecewise linear functions. These are lines, several lines put together. The dimension of the Voronoi diagram in 2D is one-dimensional. So it's a set of lines. And then you have intersections of lines. For example, you have here a triple intersection, triples, 4, and even 6. See? Okay.
Okay.
Can you imagine this Voronoi diagram in 3 dimensions?
Then the boundaries would be two-dimensional, right? Because, well, the boundaries, the lines which draw the Voronoi diagram, because the boundaries between each class is two-dimensional, because the space we have is three-dimensional, right? I don't know if I explain myself.
Well, do you all agree? I mean, the boundary, the discriminant boundary between 2 points in 3 dimensions, it's a plane. And then the polytopes in 3 dimensions are formed by sides, two-dimensional sides. You see? So in 2 dimensions, we have a set of lines. In 3 dimensions, we have a set of planes, sides, in fact, because are like bounded planes. It's okay. And in more dimensions, we have an hyperplane. The dimension of the Voronoi diagram is 1 dimension less than the space. So from 3 dimensions, we cannot refer, well, it is not feasible to refer to the Voronoi diagram because it gets quite complicated. You see?
Yes, but is there like any examples of 4-dimensional or more Voronoi?
We cannot plot them.
Yeah. Okay.
We can
But
write expression.
But even if you cannot plot them, can you create them in some problems?
You could, but I mean, imagine.
Yeah.
To represent this Voronoi diagram, you need to have you need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 linear functions. But for each linear function, you need to specify this linear function goes from this point to this point only. This linear function goes from this point to this point only. This linear function goes from this point to this point only. This linear function goes from this point to infinity. You have to specify all this. Just for 2D. What happens in 3D? Well, you have a much more, for the same number of points, you have a larger number of planes. For each plane, you have to specify not 2 points, but a number of sides to limit this plane, just to specify what previously was a segment. You see?
Yes, I see.
In 1D, you have a segment that can be open. In 2D, this segment becomes a polygon. You see? If you move another dimension, this polygon becomes a polytope, and so on. So it quickly explodes just to represent the information. So Voronoi diagrams, you cannot represent them in more than 3 dimensions. It's crazy. It's okay?
Okay.
Nevertheless, they exist. More questions? Just because they exist, and just because they are important, and just because in more dimensions this diagram is quite difficult to represent, we have other instruments to do something similar. The most important of them is what we call the Delaunay triangulation. The Delaunay triangulation, it's a structure very, very related to the Voronoi diagram, but instead of, because in the Voronoi diagram, we are characterizing the regions that correspond to each prototype, and we are characterizing the boundaries explicitly. In the Delaunay triangulation, we are going to establish relations between the points according to the Voronoi diagram in the following particular way. In fact, we define this Delaunay triangulation as a graph, undirected graph, in which the nodes are the points in P, and the relations in the graph correspond to Voronoi polytopes whose intersection is not empty. In other words, for example, here, this point and this point are related because the intersection of the two polytopes, which is this line, is not empty. So, because these two polytopes intersect. Okay? By the same reason, this point here, and this point here are not related because this polytope and this polytope do not intersect. So there is no arc from these 2 points. Okay? So the relations in the Delaunay triangulation exist. What they mean is that there is a segment or whatever in the Voronoi diagram between these 2 points, but you don't specify when this segment is, just that it exists. You see? The good news is that it's much easier to represent and to keep in memory a triangulation. It's very, very easy. You only need the points and the relations. Even in an arbitrarily large number of dimensions. I mean, the representation of the graph does not depend on the dimension at all. You see? This is the good news. The bad news is that computing the triangulation is as hard as computing the Voronoi diagram. It's okay? If we consider the Voronoi diagram as a graph, we can say that these two graphs are dual. If we consider that I mean, when we say that 2 graphs are dual, when the nodes and arcs of one graph corresponds to arcs and nodes of the other. So in a way, we can consider these 2 graphs as dual. The information in these 2 structures is the same. Okay?
Okay.
No questions? Okay, let's go on. We were talking about neighbors and we introduced the nearest neighbor classifier. And the nearest neighbor classifier is very related to the minimum distance classifier. And this is also very related to the Voronoi diagram and similar structures. Okay? Okay, there is still another step in this, or another member of the same family of classifier. This member is the one that is called the K nearest neighbors classifier. Well, take into account that when we use the nearest neighbor classifier, what we are saying is that, well, we have examples, representatives of each class. And then when we are going to classify an input point, the only thing we do is to check our database, see what is the example that is the closest, and then we assign the class of the nearest neighbor, the nearest prototype. Well, this this can be a good rule, but sometimes this rule can be not as good. For example, let's imagine the following problem. One dimension. And in this dimension, I have two classes. Imagine that these two classes are class 1, it's Gaussian, and class 2 is Gaussian as well. They are both Gaussians, but we don't know. It's okay? The only thing we know is examples. We have examples that belong to one class and examples that belong to the other class. It's okay? If we take examples and compute the mean and use the minimum distance classifier, then more or less we will obtain the first mean around this point and the second mean around this point, and then the minimum distance classifier will give us more or less this boundary, which is very, very close to the optimal boundary given by the two Gaussians. Do you see that? Do you agree?
Yes.
Okay. Now imagine what would happen if we use the nearest neighbor classifier. Well, the nearest neighbor classifier uses several prototypes. Imagine that we have this, 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 and this from class in the left, and this, for classes on the right. This can happen because these two Gaussian have overlapping. It's okay? What would be the nearest neighbor classifier in this case? So I will have a boundary here, another boundary here, another boundary here, and then I will decide class 1, class 1, class 2, class 2. You see?
Yes.
So very different from the optimal one. So nearest neighbor here is worse than minimum distance if we appropriately select the only representative. So in these cases, typically when we have overlapping between classes, in these cases, the nearest neighbor classifier can have behaviors like this. Why? Because perhaps some examples in my data set can be examples that belong to overlapping regions. Or perhaps I can also have some noise in my data. Imagine that if I collect my examples and I have errors, then these errors will be translated into the decisions. It's okay?
Yes.
Can we improve that? Yes, we can. And one possible way of improving that is by defining what we call the K nearest neighbor classifier, which corresponds to the following. Instead of computing the nearest neighbor, we compute the K nearest neighbor. Not only the minimum, but the next minimum and the next minimum and up to the K. It's okay? And then what do we do with these K neighbors? Well, let them vote. It's okay? And once we have the labels of these K nearest neighbors, we take the majority label, the class which has the majority among these K neighborhoods. Formally, this part is the same as for the nearest neighbor, but now we define what we called the K neighborhood in P, the set that contains the K closest prototypes in P. Then this amount here is the number of prototypes in the neighborhood that belong to class I, and this is the number of neighbors that belong to other classes, to any of the other classes. And we decide class I to the one which is maximum. This corresponds to voting. It's okay? If K equals to 1, then we have the nearest neighbor. So this is a generalization. It's okay? Do you understand that? It's also very, very intuitive. I take neighbors, I check the labels of these neighbors, and I decide which label is the majority label. Well, this is a quite poor plot, because this plot should be, okay, this is a set of points. This is, I can see, I think this is the first neighbor. This is the first neighbor. Then the three neighbors is this one here. That should be like this. So it's not clear, I'm sorry. And the other one is the 6 neighbors. Well, the important thing is that now is very difficult to plot by hand. It's difficult to plot by hand, but it has to be easy to see that the boundary now is also piecewise linear. And why is piecewise linear? Well, it's piecewise linear because even though now we have a votation, the votation is done according to sets of points. For example, let's start well, this is not a good plot to see that, but I mean, in the same way that in the case of one nearest neighbor, the boundary corresponds to the place that is at the same distance from 2 points at each side of the boundary. This is in one nearest neighbor. In k nearest neighbor, the boundary corresponds to a region in which voting favors, if you go through this, then the votation favors one class, and to the other side, the votation favors the other class, which means the following. It means that the third, let's put an example. 3. Okay. If we have this boundary, it means, forget about this. If we have this boundary, it means that the third and fourth neighbor have to be these two. So in the case of 1, this is the first, and this is the second, but they are at the same distance. So this is 1, 2, or 2, 1. It's the same. You see? All other prototypes are farther from than these two. In the case of 3, this is the third, and this is the fourth, or the other way around, in such a way that the other two, perhaps they are here, and here, let me check. No, it can be like this. It's difficult. It's difficult to plot, but I don't know if you understand what I mean. So the 2 points that define all different segments of the boundary are, in this case, the third and fourth neighbors when k is equal to 3, and in the same way for any other value of k. At the end, the boundary has to be formed by a piecewise linear function. It's okay? Questions? Okay, let's go. Intuitively, using nearest neighbors, using these rules, we will obtain good results if we have data sets that are representative. If we increase the number of k, then we have the importance of points which can be misleading is reduced. For example, it's interesting to see what happens in the previous example when we had, remember, 2 Gaussians with overlapping, and we have a set like this. I plot only 3, but imagine many of them. And you can have things like this. What happens in this problem if we use the k nearest neighbor instead of the 1 nearest neighbor? Well, the thing is that in this area of overlapping, if you take a large number of K of neighbors, and if you have many of them, I mean, imagine I have only plot here 6, but imagine thousands. If you take many of them, it's quite likely that on the left of the optimal boundary is quite likely that the majority of neighbors come from class 1. And by the same reason, it's quite likely that on the right of the optimal boundary, it's quite likely that the majority of the neighbors come from class 2. Why? Because the posterior probability corresponding to the optimal classifier, I don't know what is this probability, but if my set is representative, well, then I should have more 1 class points at this region and more 2 class points at the region. Just because of that, the votings will be gained by this class on this side and by this class on this side. You understand that? This can in fact be proved with some remarks. It's okay? What I'm saying? So the idea is that when we take higher K values, the voting becomes more representative if we have enough points. And now the question, but this would happen always? It's always, imagine you have a problem, you have examples, any number of examples, and you want to implement the K nearest neighbor rule. Then you can take K as high as you want. I mean, can you always improve the result by raising K or not? Why not? Can anyone ask? Answer? Do you think that higher K values will always improve the results? No? One? Not always. Okay, why not? Why not? No? Okay, let me just say something. I mean, well, intuitively, if we take more and more neighbors, then votation may become more accurate. But why you are voting about the classification of a point X? Well, it's because you are close enough to this point. I mean, the closer to this point you are, the fairer your vote is. You know what I mean? Imagine we live in a city. We live in a city. A city of 100,000 inhabitants, for example. And we are going to make a votation to decide whatever. And we go to a place, to a street, to a house, and then make a votation. We take neighbors and make a votation. The larger number of neighbors we take, the more accurate is this votation about whatever. But if we increase the value of k too much, then some of these neighbors will be very far from this point. You know what I mean? So if you increase the value of k too much, some of these neighbors will be very, very far away from x. And then these votes would be useless because they do not represent at all what happens at point x. It's okay?
Yes.
Okay, this is in fact the way it is. Well, this is just another example. This corresponds to two Gaussian functions, one Gaussian, the other Gaussian. You have here the optimal classifier, the Bayes classifier, which is this parabola. The one nearest neighbor classifier has this wrong region due to this point. And the k nearest neighbor classifier for 3 and 6 don't have this. And they, as you can see, they get close and close to the optimal classifier. This is for two-dimensional data. Okay? Okay. And this is what typically happens when we use the family of k nearest neighbors on a given problem. In practice, what happens is more or less the following. This is the error. When you start with k equal to 1, you have a certain value. Usually, when you increase k, you get less and less error, usually. And then from one point at a given value, then usually the errors becomes to increase or to oscillate. Why? Well, because more or less the distance of the kth nearest neighbor from this point on is too far for this problem. Well, for this problem and for this size of the training set, because the higher the training set, the more you can increase the value of k. It's okay? If you double the number of the size of the training set, then the distance of the k nearest neighbor gets smaller. It's okay? Equal or smaller. Okay?
Yes.
We have run out of time, so if you have questions, today is 17. Next class would be on Monday, and we will present the next lab class on Wednesday. You have to organize yourselves in pairs. You know that we have two groups of labs. Probably the first lab session would be a joint session, but you have to organize yourselves in pairs in each of the 2 lab groups. It's okay? We will do that either on Monday or maybe on Wednesday. But just be prepared. Questions? No questions? Okay. See you on Monday.
Bye.
Yeah.